3.6 Finding Roots of Polynomial Equations, Day 2. Today you will identify the multiplicity of roots, you will use the rational root theorem to solve equations, you will factor simple expressions that require complex coefficients, and you will understand that complex solutions always occur in pairs. Example number 1 says solve by factoring a GCF first and then using the quadratic formula or the square root property. So both of these are divisible by 2x. So if we factor out our GCF of 2x, we are left with 2x times x squared plus 9. We can then solve using the zero product property. So we're going to set 2x equal to 0, and we're going to set x squared plus 9 equal to 0. The inverse of multiplication is division, so we get x is equal to 0. The inverse of addition is subtraction, so we get x squared is equal to negative 9. The inverse of squaring something is square rooting it, so we get x is equal to plus or minus the square root of negative 9. So we know that x is equal to plus or minus 3i. So we just solved for our solutions, which are x equals 0, x equals positive 3i, and x equals negative 3i. You can see here the 3i is a complex solution, and it will always happen in a pair. So you will always have a positive and a negative of that solution. We usually factor using only rational numbers, but this equation can be solved by factoring with complex numbers. So looking at the same problem that we looked at previously, 2x to the third power plus 18x equals 0 can be factored using a GCF to 2x times the quantity of x squared plus 9 equals 0. We then know if we had the difference of two perfect squares and we had x squared minus 9, it would equal x plus 3 and x minus 3. So because it's a complex number, we can rewrite those factors as x plus 3i and x minus 3i. Then we set all three of those solutions equal to 0, like we did previously, to solve for our roots or our x-intercepts. And when we use our inverse operations, we get x equals 0, x equals negative 3i, x equals positive 3i. Remember, complex solutions always occur in pairs, a plus or minus bi. So we have our negative 3i and our positive 3i. When we look at example 2, it says solve by factoring. So if we had the difference of two perfect squares, x squared minus 25, we know that that would factor as x minus 5 and x plus 5. So when we're working with a complex number, we will have x plus 5i, x minus 5i. We then set those both equal to 0 using the zero product property, our inverse operations. We subtract 5i to get x equals negative 5i. We add 5i to get x equals positive 5i. List all the possible rational roots, then find all of the roots. So when we're looking at example 3, in order to list all of our possible rational roots, we list our p's over our q's. So remember, our p's pertain to our constant at the end. Our q's, we have an invisible 1 in front of this, pertain to our coefficient of our first term. So when we list the factors of 8, we have 1 times 8, 2 times 4. And remember, there is a plus or minus in front of all of these. And the factors of 1 are just 1. So our possible roots are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. But it asked us to find all of the roots. So now what we can use is we can use our synthetic division. So take the coefficients of our terms, we aren't missing any terms, We then can choose any one of these possible zeros to find the actual zeros. So I'm going to try -1. So you drop your first term, you multiply 1 times -1 is -1, and then you add. -1 plus -1 is -2. Multiply, -2 times -1 is 2, add is 4, 4 times -1 is -4, -4 plus -4 is -8, -8 times -1 is +8. When we add those together, we get a 0, so we know that one of our real solutions is -1. We can then continue our synthetic division directly from this next line. We just need to choose another possible 0, and I'm going to choose 2. You can choose any of these numbers up here. -1 already worked. You could use it again, but in this case I'm going to try a 2. Drop your first term. 1 times 2 is 2. Add those up, you get 0. 0 times 2 is 0. Add those up, you get 4. 4 times 2 is 8. -8 plus 8 is 0 again, so we know that x is also equal to 2. We now have taken our polynomial that was to the 4th degree by using synthetic division. Our first time, rewrote it as an x cubed. When we rewrote our after synthetic division the second time, we now have a quadratic equation of x squared plus 4. We can nicely factor this. X plus 2i times x minus 2i. We set each of those equal to 0. X plus 2i equals 0. X minus 2i equals 0. So we get our last two roots, which is -2i and +2i. So our degree was the 4th power. We should have 4 roots, and we have -1, +2, -2i, and 2i. Example number 4 says list all the possible roots and then find all the roots. So when we use our p's over q, for this function, we first want to make sure that it is in standard form, which it is. Our highest degree is a 3, which also tells us we should have 3 roots, and we end with our constant of 5. So remember, our p pertains to our constant. Our q is our leading coefficient. So the factors of 5 are 1 and 5. The factors of 2 are 1 and 2. So our possible roots are plus or minus 1, plus or minus 1/2, plus or minus 5, and plus or minus 5/2. Remember, those are our possible real roots. We can have our complex or imaginary roots. To find all of our roots, we want to use synthetic division. So we use our coefficients 2, -9, 14, -5. And we choose one of our real roots. If I try a 1, drop your first term. 2 times 1 is 2. -7, -7, and 14 is 7. 7 plus 5 is 2. We know that +1 is not a root, so we need to try again. So this next time I'm going to try a 1/2. It's my next positive term in my list. You can try any of the numbers in the list, and the more practice you do, the better off you will get at guessing. Drop your first term. Half of 2 is 1. -9 plus 1 is -8. Half of -8 is -4. 14 plus -4 is 10. Half of 10 is +5. -5 plus 5 is 0. So we know that one of our roots is x equals 1/2. We then know that from a cubic, we now wrote a quadratic, and when I have a quadratic equation, I can simplify by factoring, if it's factorable, the quadratic formula, looking at this problem, I know they're all divisible by 2, so to make things easier on myself, I'm going to factor out a 2 first, and I get x squared minus 4x plus 5 equals 0. I then know that there is no combination of negative or positive numbers when I multiply 1 times 5 that would add to get me a negative 4. So this is not factorable any further. So I'm going to use this quadratic, the simplified quadratic, and plug it into the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So a negative and a negative change to a positive 4 plus or minus the square root of 16 minus 20 all over 2. 16 minus 20 gives me a negative 4 underneath my radical. I know that negative 4 is equal to the plus or minus 2i over 2. I now have my 3 terms on the outside, so I use my heart, and I can reduce it to x is equal to 2 plus or minus 1i over 1, which is the same thing as saying 2 plus or minus I, and I just found my other 2 roots. So my 3 solutions are x equals 1/2, x equals 2 plus I, and x equals 2 minus I. I check looking at my highest index. I should have 3 roots. I found all 3 roots, and we are finished.